Hey everybody, this is Mr. Parliament, and this is a video on the point particle assumption versus the extended rigid body assumption and how it relates to some of the equations we've been working with. So really what first prompted me making this video is some students asking about this equation right here. Angular momentum is equal to the cross product of linear momentum and the radius at which the object is at from the pivot point. So, quick introduction of the point particle model versus extended rigid body model. The point particle model assumes that an object can be treated as if it were an infinitesimally small point in space. And that's actually an assumption we've used most of the year. Everything up until our rotation unit, we were treating objects as if they were tiny points in space. And that could be because literally they are tiny points in space, like a proton or an electron or an atom or something. And there's really kind of only one way I can apply a force to that thing. Just come and apply a force straight that way. And if I apply a force this way, the object is going to accelerate that way while my finger is touching it and then continue on at a constant velocity. If we have a larger object like this one, we've got more options to the way in which we can apply that upward force. So one example is if I apply that force kind of right near the center of mass, like along the center of mass, kind of going through the object, then if I apply a force like that, this object is going to accelerate in a straight line this way. And then, of course, after I let go of it, it'll move at a constant velocity. And that is an example where I can treat this large object as if it were a point particle. So really, most of the problems we did in class weren't really tiny objects. They were much larger objects that we could apply lots of different forces to, but because we just so happened to apply a force directly in the middle of the object, it behaved as if it was a single point moving about that center of mass. Now, we've talked about different problems where we can apply a force off-center on an object. So I can apply a force here. And if I do that, two things are going to happen to this object. One is it's going to start rotating. The other is that it will also start to move in a straight line like it did the first time. So it would rotate while moving. All right, so there's a little bit about point particles versus extended rigid bodies. We've talked about extended rigid body diagrams where we treat an extended rigid body as if it were a line. And that line helps us show not only what forces are being applied, but where they're being applied at. Point particles, we just use a force diagram where our object is a single dot. All right, so there's a little bit about the difference between the two. The reason why that's relevant here is that this equation, angular momentum is equal to the cross product of linear momentum and radius, is an equation that specifically works with the point particle assumption. And we'll talk about why in a bit here. All right, so first thing I want to talk about is actually question 1b on worksheet 6.4. And that question asks you to find the angular momentum of the Earth as it orbits around the Sun. So in order to find angular momentum, I started with moment of inertia. The moment of inertia of a sphere rotating about its central axis is 2/5 times the mass of the object times the radius squared. But we're not talking about an object moving about its central axis. We're talking about the Earth orbiting around the center of the Sun. So I'm going to go ahead, I'm going to zoom out here. Zooming out, zooming out, zooming out. The Earth gets smaller and smaller and smaller. And if I zoom out far enough, I'll see the Sun right here. So the Sun is obviously much larger than the Earth. It is also very far away from the Earth. The radius of the Earth is much, much smaller than the radius of the Earth's orbit around the Sun. So Essentially what I'm doing here is I'm shifting the axis of rotation from the center of the Earth to the center of the Sun. And we can do that with parallel axis theorem. So you may have noticed that on my key for 1b on worksheet 6.4, I just used m r squared, where r was the radius of the orbit, for the moment of inertia of the Earth. And I want to talk a little bit about why. So I used Wolfram alpha, and I asked it to divide the radius of the Earth's orbit by the radius of the Earth itself. And the Earth's orbit is about 23,500 times larger than the radius of the Earth. So this distance is way greater than this distance right here. So really, this part of the equation is going to go away. This is a much bigger radius, and it's squared, so that's going to further increase the discrepancy between the two. And our equation basically just becomes moment of inertia equals mass of the Earth times the radius between the center of the Sun and the center of the Earth squared. So that's one way you could find the moment of inertia for the Sun. You could also just kind of look at this and realize, oh hey, when we're this far away, when we're this zoomed out, the Earth looks like a small point in space compared to this massive distance, so we can treat it as a point particle. That point particle equation is actually really easy to derive with our definition of moment of inertia. We define moment of inertia as the sum total of all the masses times their radiuses squared. We also had that as an integral form of the integral of r squared dm. We actually don't need the integral form here, because if our m is just the Earth, and it's at more or less one single fixed radius from the Earth, which is this what we call d here, or sorry, the Earth is one fixed distance from the Sun, then this sum total is just going to be equal to m d squared. So that works as long as we can assume that the difference between the masses, the radius of the masses on this side of the Earth versus this side of the Earth are very small, which is true here. All right, so once you have moment of inertia times angular velocity gives you the angular momentum. Blake Hogan sent me an email, and he pointed out that for this problem, you can use angular momentum is the cross product of linear momentum with the radius, and you get the same value for the moment of inertia of the Earth. So I went, so you get the same value for the angular momentum of the Earth around the Sun, sorry. So I went ahead and solved it both ways. So moment of inertia is md squared. So angular momentum is moment of inertia times angular velocity. So that would give you omega times m times d squared. If you use the cross product of linear momentum and distance between the objects, usually this is r, but we've been calling it d here to distinguish between distance from Sun to Earth as opposed to simply radius of Earth. So take that cross product, you'll get m times v times d. Tangential velocity, we know, is equal to the angular velocity times radius, which again in this case is d. Plug that into this equation, we get omega times m times d squared is our angular velocity. So both of those did get us the same answer. Next thing I want to talk about is actually a question that Travis had about question 5 on worksheet 6.4. On my key, I solved her work as the difference in rotational kinetic energy. And he solved it as the difference in terms of the difference in translational kinetic energy. And both, in fact, get you the same answer. And the reason for that is for a point particle, where your moment of inertia is mr squared, your rotational kinetic energy is equal to your translational kinetic energy. They're actually the same thing. So our equation for rotational kinetic energy is 1/2 I omega squared. And our moment of inertia for a point particle is mr squared. So we can plug that in here. We get 1/2 mr squared times omega squared. We know that tangential velocity is omega times r. So omega squared times r squared would give us v squared. So ek rot equals 1/2 mv squared. And of course, we know that translational kinetic energy is 1/2 mv squared. So that works because we're treating the Earth as a single point right here. And that point is moving at some velocity v forward. It is also, you could also consider it as having some angular velocity around the sun. And either way, you can use either the linear values to find the kinetic energy or the rotational values. Now I want to look at our figure skater problem, problem 2, to see why these two equations don't work for things that aren't point particles. So I've got our skater, our figure skater, and she's spinning around. And I drew some of these gray boxes here, one around her head, one around her hand, and one around kind of halfway down her arm. So if we were to try to use angular momentum is the cross product of linear momentum and radius, I think it would really quickly beg the question of, well, for what part of her? Like if we look at the hand, that's going to have some linear momentum at some radius. If we look at the arm, that's going to have a different linear momentum at a different radius, and her head as well. So since we have all these different objects would have different linear momentums and different distances from the pivot point, different r's, well, we couldn't use this equation. Similarly, we can't use kinetic energy as 1/2 mv squared for the skater because it would again beg the question of, well, what part of the skater? Her hand has a different tangential velocity than her arm. It's tracing out a larger circle every rotation. And both of those would have a different linear velocity than her head. So specifically, using this equation for angular problems and this equation for angular problems assume that we're dealing with a point particle. So hopefully that clears that up a little bit. If you have any further questions, feel free to email me. Thanks. Have a great rest of your day.